Howdy folks, we are going to be taking a look at extreme values today. So the idea of extreme values are that some functions that we are interested in taking a look at will have values that are part of part of the function over the course of it that will reach lowest possible or highest possible values. Now, we're going to get into a little more specifics in the terminology there, and sometimes you care about like a locally low point versus an absolute low point. But you have already bumped into these during your learning that you've done with all kinds of different functions over your pre-calculus courses. So the idea is that if we took something like, for instance, a parabola. So if we take this parabola right here and say that that point is at 1, 1, then that point, which we lovingly refer to as the vertex, is the lowest possible point of this particular upward facing parabola. So if we were to write its domain, and it's not too much special there, it would just be x values, all real numbers. And then for the range, the y values are going to be greater than or equal to that positive 1 value, and also be a part of all real numbers. So as such, we kind of have this idea that there are no values of 0 or -1 or -2 for the y values. That is the lowest possible value. Now, the reason we're covering this in calculus is because this idea of a lowest possible value is going to fit hand in hand with something else that we've already seen, and you might already intuitively know from what we've covered so far in calculus. So we're going to study this knowing that it's going to prepare us specifically for doing graphing and optimization problem solving. Those two things really go quite hand in hand and are married to this idea of extreme values. So just to make sure that we're referring to the same thing at the same time, let's get into some kind of definitions of what's going on here. So if you have an absolute maximum, some people will call it a global maximum, that means that that function will never ever over the entire course of its domain give you a range value or a y value if you wish that is larger than the one that you're currently looking at, or more positive if you wish. So there is nothing on that side of the number line that would exist past the one that you're currently looking at. So the way that it's described here is that there is an absolute maximum at a value c. So c is just generic, let's pick this value. If this generic value is actually an absolute maximum, then that's only the case if the y value at c, or the function's value when evaluated at c, is greater than or equal to the function at every, so this upside down a here is basically at every or for every x that is an element of D, where D is the domain of f. So it's basically saying that there is no other x value in the domain that will ever give you a value that is greater for its range value than the c value that you've already found. Now, you'll notice that this is greater than or equal to, so it's okay to have absolute maximums occur at multiple positions. So if, for instance, we had a downward facing quartic, something like this, and if I had drawn it nicely and those 2 points were at the exact same height, then they would both count as an absolute maximum for this particular function. So it is it's entirely okay for that sort of thing to be going on. Don't fret that an absolute maximum has to be a singular point that fits that description. It doesn't. So minimum is going to be no big shock there. Basically the same thing, except for it is going to be that the y value that you find is less than or equal to every single other y value, where as long as you're staying with x's that are in the domain, which makes sense because otherwise you can't evaluate the function. So pretty straightforward. All right, now this is a concept that may or may not resonate with you in terms of how important it may be later on. But there's going to be a local maximum or minimum. You'll hear me because I think I know what I'm doing when I talk Greek, apparently, or Latin. I guess in this case it's Latin. So the maximum and minimum, we're going to talk about the plural versus the singular. So if you have a piece of data on your computer, it's technically a datum. UM ending is actually an A ending when you talk about the plural of it, if it's a noun. So maximum, minimum, if we're talking about more than one of them, maxima, minima. I try to use them correctly, but of course I forgot what language I was even using there at the beginning, so I wouldn't rely on my ability to do that properly all the time. But there is a method to it, and it's not just to be confusing. It is because those words are ripped from another language where that is a singular plural rule. So if a function f has a local maximum, so singular I guess, at c, if f of c is greater, or it does, if f of c is greater than f of x, not for every x that's a part of the domain, that's an absolute. This one says when x is near c, and that's one of my favorite / not favorite things to talk about when we're doing this sort of thing, is trying to describe to somebody what near means. So the idea of near is really, it doesn't sound very mathematically sound. So it basically means if you're at a point C, which if we took, for instance, this little point right here in this particular picture that I have down here, near means go a little to the left, a little to the right, kind of look around, see what's going on. That's what near means. It doesn't mean that you go check way over here and you're like, hey, wow, this stuff's higher over here. So therefore, this can't be a local maximum. So you basically kind of like, I don't know, it's kind of like you're one of those nervous people that's going and exploring a high mountaintop or something like that, and you want to know if you're in the highest point where you are, so you look a little to the left and you look a little to the right, and you don't worry too much about exploring too far or really checking it out. You're just kind of, as long as you know that right in the vicinity that you're in, you're on the highest point, then that's what you care about. So that's what near is kind of referring to, is directly to the left and the right of the position you're currently interested in. So you have a local maximum if basically when you go a little bit left, a little bit right, there's no point that's higher than you are. So that's a local max. If you do the same thing, like what's going on down here, and you go a little bit left, a little bit right, and you also determine that there are no points that are lower than you, then you would be a local minimum in that particular case. So absolute maximum, nothing is higher than you. Absolute minimum, nothing is lower than you. Notice it's what's lower or higher. Equal is fine. And then local maximum or minimum, sometimes referred to as relative. So just to make it really awkward, we have pairs of wording. So you have absolute or global, and you have local or relative. I tend to use absolute and local probably as my go-tos. Depending on the text you may be looking at or some of the stuff you see online, it's the same, whether you talking about absolute or global or local or relative. All right, so how's this all relate to some other stuff? Well, first, before we get into that, extreme value theorem. This is kind of the worst. So it's not the worst. It's actually really, really simple, but it's not simple to prove, and we're not going to do it. And it's kind of an awkward thing to talk about. So if f is continuous on a closed interval from a to b, then f attains an absolute maximum value and an absolute minimum value at some number d and c and d in a to b. All right. So all that says is that if you are going to take some big function. And in this case, we took a big function that starts over here at A and ends over here at B. And we're saying that no matter what this function is, if it is continuous, which we just talked about the definition of continuity in the last video, if it's continuous, we can draw it without lifting our pencil, then there is, at some point along this function, an absolute maximum and an absolute minimum. You cannot draw a function that does not contain an absolute maximum or an absolute minimum value if it's continuous and closed. So closed interval. If it, of course, goes on forever, for instance, a linear function is a very simple example of something that kind of doesn't fit this, but it doesn't fit it for very good reasons. So if we have a linear function, do you know what? I should remember, I can do this and then I think, yeah, if I hold it, nice straight line. All right, so a linear function, basically the idea there is, oh, well, it just keeps going and going and going and going in both the positive and the negative directions, and it's never going to have an absolute minimum. It's never going to have an absolute maximum, because it will just keep getting larger to the right, and it will keep getting larger negative or smaller to the left. All right, so there's obviously counterexamples to this, except for if you read the extreme value theorem carefully, there is a reliance on this thing being a closed interval. So if we do the same thing and say, oh, but this is only allowed to go from A to B, well, then this, congratulations, is now your local minimum, and this is now your local, absolute minimum, and that other one is your absolute maximum. In the funny little picture I have here, there's an absolute minimum right here, and there's an absolute maximum right there. And again, you cannot draw a function that is continuous, so without lifting your pencil or pen, that will basically, if it is between two endpoints, you cannot draw one that does not have an absolute maximum and an absolute minimum. So that's what extreme value theorem says. Fermat's theorem is where we start kind of seeing a relationship to what we're talking about with respect to derivatives. So Fermat's theorem says that if there is a local maximum or minimum at some c value, and if the derivative exists there, then the derivative is 0. So this one is kind of funny because there's actually two things that has to be going on there. Basically, you are told that there is a maximum or minimum, and it's differentiable, or it has a derivative that is a numerical value. It exists. If that numerical value exists, it's guaranteed that the numerical value is 0. The numerical value does not have to exist, and it can still be a local maximum or minimum. So what's in red text below there, it says that the converse of Fermat's theorem is not true. So a converse is, so if I was to make it as simple as I could, if A implies B, the converse would be B implies A. So sometimes you have a statement that is, when you say, okay, well, if A is true, then B is true. But if B is true, then A is true. That is something where the original statement and its converse would both hold true. So in the case of Fermat's theorem, we have that there is a local minimum at C, or maximum. And if the derivative exists, then the derivative is 0. Just because the derivative is 0, though, does not mean there's a local maximum or minimum. So the converse is not true, and you can see that in a couple little graphical examples down here. Some funny things are happening. So at this particular spot, it's pretty easy visually to tell that the derivative at that spot, well, that was kind of wonky, but the derivative at that spot would end up being 0. So if I were to draw in a tangent line there, it looks like it's a nice horizontal tangent line. Derivative must be 0 at that particular spot. Great. So that's what's going on there. However, that is definitely not a local maximum or minimum. If we look at this value and we go a little bit to the left or we go a little bit to the right, We go a little bit to the left, and there's, or sorry, that's the right-hand side. A little bit to the right, and the values are higher. We go a little bit to the left, and the values are lower. What that ends up meaning is that the values at that particular spot, nearby values can be both greater than or less than the value we're currently looking at. It's not a local minimum, not a local maximum. But the derivative is 0. So it's definitely not true that the converse holds, because we found a counterexample. Also, though, this idea that the derivative has to exist for it to be a maximum or minimum is not necessarily true, and that's not really what this is implying at all. It's basically saying if you do have a maximum or minimum and the derivative exists, well, you can have a maximum or minimum, like this minimum right here, where the derivative does not exist. So the derivative doesn't exist. We can tell that because if you come in from the left and you come in from the right, those are two different slope values. So they're not going to agree with each other at the lowest point down there. So we're going to get that there is no derivative. The slope here is like, I guess this is a -1 and this is a +1. Those are, scale is a little bit funky, but it's 1 over 1 up in terms of rise and run. So we would find that you can have local maximums or minimums even if the derivative doesn't exist, and you can have derivatives of 0 that don't give you local maximums or minimums. All Fermat's theorem says, as a rewind, is if there is a local maximum minimum and if the derivative exists at the same time, then the derivative has to be 0 for that to be true. All right, so just a few more definition things. So we have the idea of critical number, critical point, stationary point. Now this is awful because they're all very similar in terms of the naming. So a critical number, I'm just going to read, I know you can, but the x value on the interior of a domain of a function f of x for which the derivative is equal to 0 or the derivative does not exist. So if you find in your function that there is it's basically, hey, there's an interesting position in your function and an interesting x value. At this interesting x value, the derivative is either 0 or it does not exist. This kind of corresponds with the idea of Fermat's theorem, but it kind of goes a little bit beyond that as well, because it, in the idea of Fermat's theorem, it specifically you needed to have, or you knew that the derivative was going to be 0. We're kind of saying, well, derivatives of 0 are interesting and need to be looked into, even though it's not a guarantee of anything. Same thing with derivative not existing. It's all kinds of reasons why that could not exist, but as we saw with the absolute value function, there may be a reason that has to do with minimum or maximum values. So critical number is the x value. So that's really important because the next one is critical point, and it basically is the exact same thing, but it's the point. It's the x comma y. That's really all the differences between being asked to state a critical number and being asked to state a critical point. Critical numbers are the list of the x values that fit this, and critical points are x comma y positions where you have this same set of conditions fitting. The last one is stationary point. So stationary point is any point on the interior domain of a function f of x for which the derivative is 0. So you'll note that the difference between critical point and stationary point is that you actually have to have the derivative existing and being 0. You're not allowed to have this derivative does not exist anymore. There's probably less times where the stationary point is referred to, so maybe not quite as important to remember that one, but it's that's what it is nonetheless. All right, so we can find these critical numbers both graphically and algebraically. All right, graphically is the nice way. So if somebody supplies a graph to you and you're like, oh, critical numbers are where your derivative is 0. Bam, bam. All right, so, or your derivative does not exist. Nope, it's okay everywhere else. So we found the critical numbers. The critical numbers in this case are x is equal to 0 and x is equal to positive 1. Great, done. Now, that's wonderful if you have a graph to work with. If you do not have a graph to work with, and we are instead starting with this function. So this would be f of x is equal to 3x to the 4 minus 8x cubed plus 6x squared. Now, if we are looking to find critical numbers, they are where the derivative is either going to be 0 or where the derivative does not exist. So the first thing that I'm going to do is say, I know this is polynomial, so the derivative is going to exist everywhere because the derivative of a polynomial is just going to be another polynomial, and all polynomials are continuous, so they exist everywhere, or they're continuous over all real numbers. So if we take this derivative, we're going to get 12x to the 3 minus 24x squared plus 12x, and of course this is working out in a very nice way for a very particular reason. So the idea here is we want to figure out where this thing is either does not exist or where this thing is equal to 0. So we said that it doesn't have an x value where it doesn't exist. So instead, ooh, I think it was acting up there. So instead, we're going to take this and set it equal to 0 and solve for when that might happen. Most of you are pretty good at this now, so I don't see this happening very frequently. But it is important to make sure that we are not removing any solutions when we're solving. So I don't like the idea of like dividing the x out because you're ignoring if x could be equal to 0, which actually in this case we know from the graph that it should be one of your options. So we factor out anything that's in common. So in this case 12x is common for each of those three terms. We're left with x squared minus 2x plus 1 excuse me, is equal to 0. So we get 12x, and then we would get two things that add to give you minus 2 and multiply to give you positive 1. So that would be x minus 1 and x minus 1 together. So it's x minus 1 squared. We get the perfect square for that quadratic part. Still all equal to 0. So when does this happen? It happens if x is equal to 0, or it happens if x is equal to positive 1, which if we compare to what we had graphically, of course, that ends up giving us the same thing. So we were able to determine where those minimum and maximum values, or at least critical numbers. The second one is not a minimum or maximum value. But anyway, that's we found them algebraically and graphically. So there is, and this is really important specifically in problem solving, but you may come up with graphing problems that give you defined boundaries as well. So it says to find the absolute maximum or minimum of a continuous function on a closed interval, it is not sufficient to find the roots of the derivative. We must also consider the endpoints. That's because, like we kind of have for, if we had a cubic, goes like this, and it goes on forever and ever. But let's make this thing so that it is only defined between particular values. So what if I said that this was the endpoint A, and this is the endpoint, no, actually I'm going to take this as the endpoint B. So, quick quiz. Where is the local minimum? Well, the local minimum's here. So, for this local minimum, there's no point that's lower there. From either side, go a little bit to the left, a little bit to the right. Anyway, well, you might make an argument that B, since it's one-sided at this point, is also a local minimum. Local maximums. There's going to be one right here. Absolute maximums. This is the absolute maximum. Absolute minimum. This is the absolute minimum. So the absolute maximum occurs on an interior point, and it's an interior point that will show up as a critical number. The absolute minimum is an endpoint, and that will not show up. When we take the derivative, it will not show up And the reason why is because there's more function that would be there normally. If we keep going out to the right, it will get lower, but for some reason, whether it's artificial or not, doesn't really matter, we are chopping off this function, so it cannot go past b, and therefore b, the y value there, is the lowest y value we will reach on this entire function. So if you have a closed domain or a closed interval that you're interested in, you need to not only find all of the potential interior points that could be interesting, you have to also test the endpoints to be able to find out whether something's happening there that you need to be paying attention to. So if we take oh, that makes me sad. I had an example, I thought. All right, so I'm going to maybe I took it out for a reason. I can't remember. All right, well, I'm going to make one up on the fly and just see how it goes. So if we have x cubed minus x plus 2 as our function, and I would like to know between a value of -1 and +2, what is the lowest value, what is the highest value. So I'm looking for the absolute maximum and the absolute minimum. So that's what I want to search for. Absolute max, absolute min. So first off, we could look for an absolute max or min by testing to see if this has any interesting critical numbers during its stretch of values. So the first thing I'm going to do is I'm going to take this derivative, and it will give me 3x squared minus 1. And so then I'm going to get that the absolute value, or sorry, the derivative, if I set it equal to 0, gives me 3x squared is equal to 1. So x squared is equal to 1/3, or x is equal to 1 over root 3, or if you want to get really picky, I guess root 3 over 3, but it doesn't really matter too much. So root 3 over 3, and I should have, and I will, fix that by putting in plus or minus. So I took the square root of x squared. It could have been positive times positive or negative times a negative. So either one of those answers would be fine. Okay. So my domain was from -1 to +1. So actually, both of those numbers are going to be okay. So they are both between those two. So I have a potential local minimum there and a potential local maximum there. And so if I want to find whether they are the absolute maximum or the absolute minimum, I'm just going to compare them. Now, we're going to get into something a little more tests, I guess you could say, to see what's going on at these critical numbers. But for the time being, all I need is the absolute max and absolute minimum for this particular problem. So I'm just going to list these things. I want to know, well, what does the function look like at -1? What does the function look like at negative root 3 over 3? What does the function look like at positive root 3 over 3? And what does the function look like at 2? Now, I might have a little bit of a regret here when it comes to the values that I ended up picking out here, but that's okay. So we have x cubed minus x plus 2. And so at a value of -1, we would put the -1 in and get -1 minus -1. So that's a 0, so that gives us a +2 there. And at the other end, because that number's easy too, I want to avoid the middle ones for the time being. So we would have 8 minus 2 is 6, plus 2 is 8 again. So I have found that on the outsides of this function, we are getting, outsides of these bounds, the endpoints here, we get +2 and +8 as the values. Now, I'm trying to think. I probably should just kind of cheese it, and I'm going to grab my calculator just to do the the cube of the root that's there, because it's if it was a square, I might not worry about it too much and just do it by hand, but I want to make sure I get values that are reasonably well done. So we're going to say it's negative the square root of 3 divided by 3. And so we're going to take that and cube it, and then minus root 3 over 3 plus 2. So if I punch that in, okay, I get 1.23. And if I do the same for the other one, now I might have made a mistake with the negative. I'll take a look at it in a second. So for the other one, I get root 3 over 3 cubed minus root 3 over 3 plus 2. So 1.62-ish. I'm going to just do that last one more time, even though it's a waste of my video, but that's fine. So root 3 over 3 now to the power of 3, and then it's plus root 3 over 3 plus 2. Yeah, I did do a mistake there. That's good. At least I went back and checked it. All right, so 2.38. So if you'll notice, we can go along and we can basically compare these 4 values that we got. So the last value is obviously our highest value, and our second to last value is actually our lowest value. So we would have an absolute max at 2,8, and we have an absolute min at, and it's going to be root 3 over 2, comma, and then it's kind of a little bit of a, I don't have an exact value for it, so it's 2.38-ish. So, sorry, that's root 3 over 3, not root 3 over 2. And so I'm going to take just a little bit of a look at, as a closing thing before I leave you, at a graph of what this would look like. Except for I don't have my graph stuff ready to rock. That's okay. I'm going to do it over here, and there. That's okay. We'll get y is equal to x cubed minus x plus 2. And so in this particular case, we have this, and I'm locking it in between -1, 2 as one of the endpoints, and my other endpoint is going to be at 2,8. And so if I put those two in, and I'm only caring about the function between this point and that point, then the highest possible value is definitely this one, and the lowest possible value is definitely this one. It ends up being at a value of yeah, exactly what we found. I don't know why I wrote down the wrong thing. So it was root 3 over 3 comma 1.62. Oh well. At least we found the right thing, but I didn't write it down properly. So I took the one from the negative for some strange reason. Anyway, we can find them algebraically. We did find them algebraically. And so that's basically the idea behind finding absolute maximums and minimums, or local maximums and minimums, and then just doing a comparison by finding the y values out at each point. All right, that's good for now. That's a lot of stuff. So I'll leave you at that. Take care.